In this lesson, I want to talk about random numbers. Many algorithms seem to use random numbers or random selections from groups. In practice, true randomness in a computer is very hard to find. Computers can do some very complicated things, but they're still just following a list of definite steps. A list of definite steps can't produce truly random numbers, so the algorithms that produce those numbers are called pseudo-random number generators. This kind of generator produces numbers that look random to you and me, but they're actually predictable. If you know the algorithm the computer is using, and you know the internal state of the computer's memory, then you could predict the numbers that will pop out. Pseudo-random number generators often are fairly predictable and their numbers repeat after a while, although the length of the repeat cycle can be pretty long. For example, you might need to generate a few million pseudo-random numbers before they start repeating. If you know the algorithm a pseudo-random number generator is using, and you see a few thousand numbers from the sequence, it's not too hard to figure out what the rest of the numbers will be. In contrast, a cryptographic random number generator produces numbers that are very hard to predict. Even if you know the algorithm and you see a few thousand numbers, you can't predict the numbers that will follow. These kinds of generators are in some sense more random than pseudo-random number generators. But for most algorithms, you don't need the extra cryptographic protection. They tend to be a lot slower, so most randomized algorithms use normal pseudo-random numbers. These kinds of algorithms are more properly called cryptographically secure pseudo-random number generators. The final kind of randomness I want to talk about is true randomness. A true random number generator uses some sort of non-deterministic process to generate numbers. For example, it might use random fluctuations in radio signals, radioactive decay, lava lamps, dice rolls, or some other complicated physical system to generate numbers. True random number generators are complicated and relatively slow, so few computers have them. And as I mentioned before, few algorithms really need true randomness. If you really want to generate a truly random number, you can go to random.org and get some numbers generated by measuring atmospheric noise. Pseudo-random number generators are the fastest and are usually good enough, so that's what most algorithms use. In the other lessons in this course, if I say random number, I really mean pseudo-random number, unless I state otherwise. In this lesson, I'll explain linear congruential number generators, or LCGs. These are the most common kind of pseudo-random number generation algorithms. LCGs generate random numbers by using this simple relationship. To create random number x sub n plus 1, you multiply a constant a by the previous random number x sub n, add another constant b, and take the result modulo a third constant m. For example, suppose a equals 5, b equals 3, and m equals 7. Let's arbitrarily set x0 equal to 0. The value used to initialize a random number generator is sometimes called a seed value. If you use a different seed value, you'll get a different sequence of numbers. To get the second number for the sequence, you plug the first number, 0, into the recurrence relation. That gives 0 times 5 plus 3 mod 7. That's the same as 3 mod 7, or just 3. That means the second number in the sequence is 3. To get the third number in the sequence, you plug in the second number, 3. Now you get 3 times 5 plus 3 mod 7. 3 times 5 plus 3 is 18, and 18 mod 7 is 4. So the next number in the sequence is 4. You can continue plugging in each number in the sequence to get the next number. When you plug in 4, you get 4 times 5 plus 3 equals 23, or 2 mod 7. If you plug in 2, you get 2 times 5 plus 3, which is 13, or 6 mod 7. If you plug in 6, you get 6 times 5 plus 3, which is 33, or 5 mod 7. Finally, if you plug 5 into the recurrence, you get 5 times 5 plus 3, which is 28, or 0 mod 7. At this point, the sequence has started over again with 0. Because each number generates the one that follows it, the sequence repeats itself. Notice that this example generated 7 values before it started repeating. That's the best you can do in this example because the modulus is 7. That modulus only allows 7 different values, 0 through 6, so those are the only values the sequence can produce before it starts repeating. This example managed to produce all 7 possible values, so it has a full period. That happens if you meet 3 conditions. First, b and m must be relatively prime. That means they share no common factors other than 1. Second, a minus 1 must be divisible by all prime factors of m. In this example, m is prime, so it has no prime factors less than itself. Third, if m is a multiple of 4, then a minus 1 must also be a multiple of 4. Let's do an example that doesn't meet these criteria. Here, a equals 4, b equals 3, and m equals 8. b and m have no common factors, so this satisfies the first rule. a minus 1 is 3, and that isn't divisible by 2, which is the only prime factor of 8. So this example violates the second rule. 8 is also divisible by 4, but a minus 1, which is 3, is not divisible by 4. So this example also violates the third rule. Now let's plug in some numbers and see what happens. I'll start with 0 as before. To get the next number, we plug in 0 into the recurrence to get 0 times 4 plus 3, which is 3 mod 8. That's just 3. Next, we plug in 3 and get 3 times 4 plus 3, which is 15 mod 8, and that's 7. So far, so good. Now we plug in 7 and get 7 times 4 plus 3, which is 31. Unfortunately, 31 mod 8 is also 7, so we're stuck in a loop. The sequence produces 0, 3, 7, and then repeats the number 7 forever. LCGs have one advantage and a few disadvantages. The advantage is that this is a fast algorithm. It only takes one multiplication, one division, and a modulus operator to generate a number. Each of those operations takes a fixed amount of time, so to generate n numbers, it would only take order n steps. The first disadvantage is that an LNG may be unable to generate every possible value before it starts to repeat itself. You just saw that in the second example. LNGs also aren't all that random. If you know the values of a, b, and m, you only need to know one number in the sequence to find all of the following values. That means LNGs aren't good for cryptography or other algorithms where strong randomness is important. The examples I used for this lesson have small values for a, b, and m, so it's easy to generate numbers in your head. In practice, to get a larger period, most algorithms use much larger values for those constants. This table shows the values used by Microsoft Visual Basic 6, Microsoft Visual C++, and Borland C and C++. You can pick your own values, or you can just use one of these. Because this algorithm doesn't give you true randomness anyway, you may as well use one of the sets of values presented here. There's one more kind of pseudo-random number generator that I want to mention in this lesson. A multiplicative congruential generator, or MCG, is simply an LCG where the constant b is set to 0. You might want to try implementing an LCG in your favorite programming language. See if you can write a program that runs the LCG until it starts to loop, and test it out with a few smaller values for a, b, and m.